Taking up right where we left off, but doing it on the computer where it looks a little prettier. We'll look at the nth degree Taylor polynomial for cosine and then see what happens when we're ambitious and we try to send n off to infinity. So first of all, let's deal with an issue of just how we write this. How do you write the general term in a nice way? Because now we're getting to a point where we want n to be variable, and so we need to have that as a general function of n. Or in other words, we can use sigma notation. How could we write this as some sort of sum of terms with an explicit formula? So one issue here is that these powers are all even. We don't want to have odd powers. This is because it's an even function. And so the way to do that is to make the general term automatically even by making it twice the index. So this is going to be term 0, this is going to be term 1, term 2, term 3, but the powers are going to be 0, 2, 4, 6. Okay, so, and then we're going to use n actually as the label for what term to stop at, but that means that it's actually going to be the 2nth Taylor polynomial. So this is a very, very common thing. When things are guaranteed to be even, you don't want to talk about an odd degree Taylor polynomial. It exists, but it's just equal to the previous even one, so why bother? Okay, so that can be a little bit of a subtlety when you have only odds or only evens. All right, so but we're on our way, so I'll put that here as well. Something times x to the 2, and so that's going to go all the way up to x to the 2n as the last term. Okay, now what's the denominator? Let me emphasize this. These are all factorials by putting a factorial symbol there, as we often do. So that matches the power. Notice it's not k factorial. This is a subtle thing about writing sequences. Even though this is the 0th term, the 1th term, the 1st, the 2nd, the 3rd, which factorial you are taking is also those even numbers that exactly match the power. So once you've figured out the power, that's really the first thing to deal with this kind of stuff. Then C is anything else that goes into the formula for the coefficients, does that match which term it is, or does it match the power in some way? So now something that matches which term it is the alternating sign. That's the last thing. Alternating signs are always expressed as -1 to a power, and that's going to be either k or k minus 1 or k plus 1, depending on exactly whether it starts with plus or minus. When it starts with a plus, and when we're starting with k equals 0, as we almost always do with power series to get a constant term in there, that's going to be -1 to the k. And so we could write this. If you don't like the summation notation, you can write it out longhand, put dot, 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 dots, and then what you put in here is the last instance of that. That's exactly where k is all the way up to n. So the price you pay for the summation notation, the compactness of that, is that you have to introduce this dummy variable. But and they're both good ways. They're both good ways to show it. Okay, so that's a little bit of technical issues of how do you write just basically big polynomials with patterns. But it's really crucial if you want to think about taking that to an infinite series. So let's be ambitious and let's define t of x to be, if we were really ambitious and had no idea how to make things rigorous, we could just let the n be an infinity and say, done, we've defined something. But of course that doesn't really define something. What does that symbol mean? Well, very much like an improper integral, if you've seen those, which often you would have at this point, that's just going to be the limit as n goes to infinity of these guys. So you look at the 1st degree, or the 0th degree, and the 2nd degree, and the 4th degree, and the 6th degree, and the 12th degree, and the 100th degree polynomial, and you look at the limits of those guys. Now that's not going to make a whole lot of sense if, as n grows, these things differ by huge amounts. But we've already observed that if x is even a decently small number, this is getting small as k increases, and this is getting small quite quickly as k increases. And so there's a good chance that we're adding less and less and less, and that maybe this limit is going to exist. But it's absolutely crucial to figure out if it really does. And more subtly, if you've worked at all with infinite series of numbers already, and I'm not assuming you have, this is a little more interesting than that even, because this is something that depends on the x. It's really a whole family of infinite sums. It could be the sum of this where x is 0.1. This is a certain infinite sum of numbers, which would be defined as the limit of 1 minus the square, comma, 1 minus this plus this, comma, this guy, and then see if there's a limit, including this. Or it could be something that might have a bit of a different flavor. It's really not what I wanted to do, though. I really wanted to copy and paste. This could be 10. Does that make a difference here? At least for a while, those numbers are growing. But, factorials grow pretty quickly, so maybe after a while the factorials might catch up, and maybe we still are adding smaller and smaller increments. Okay, the point is, it will often depend on what x is. It meaning whether this infinite sum, which is really defined as a limit of finite sums, converges. Okay, so that is a complexity, but it's a very a real thing we need to deal with. So what we're going to need to figure out is for which x's, or let's say for which values of x, that sounds more mathematical, does the limit we are using to define this infinite sum exist. That is something we're going to be very, very concerned with. Okay. What other? Let's see. So tools that we're going to need. So this, for me, this motivates a real pivot to a lot of stuff we need to go back to and do the mathematical details of before we come back and have real confidence with the main attraction, which is power series. We have we need to define an infinite sum of powers of x. Okay, so as I mentioned, that's a function of x as well as something that has the n parameter that tells us how the sum is going. Okay, so in order to understand that, we need infinite sums of numbers, like these kinds of infinite sums. Okay, in order to understand that, we really need to understand limits of sequences. So, for example, in this case, it's the sequence 1, comma, as I said, this guy, comma, let me do one more to get the idea. We've got a sequence of numbers that happens to be the partial sums so we're often interested in a sequence that comes from, well, that is, I guess, is the partial sums, just these finite sums of an infinite sum, an infinite series. But we could have other sequences, like, let's say 2, 1, 1/2, 1/4, that don't come in any obvious way from the partial sums. And we want to know, does that sequence of numbers have a limit? So that's where the typical textbooks start. This is where Stewart starts, with just limits of sequences, a section on that. Then looking at the special case of infinite sequences that are the partial sums of an infinite series that we're trying to use to define an infinite summation, we're going to do a fair amount of work on the subtleties of when those converge or when they don't. And then we'll finally come back to, okay, what we really care about here, at least, there's lots of other uses for infinite summations, is what if it was coming as the infinite sum of powers of x, in other words, a power series. So that's kind of the roadmap for the technicalities of what we're going to do. But you can understand a lot if you don't need to be super rigorous, without the technicalities. And let me show you one really cool thing we could do with an expression like this. So let's say let's assume that this sum, let me just pick it up as a, let's assume that this sum, and I'm going to put the dot dot dots on it, that's the limit of the partial sums or the infinite sum. Let's assume that this guy, that's we're calling it t of x, actually makes sense. And we'll discover, in fact, that these factorials grow so quickly on the bottom that it actually makes sense for any x. It just takes a long time to get an accurate answer if x is really big, which we've already seen. So we have a hope that since this was a decent approximation to cosine, this was a better approximation to cosine, this was even better, this is really, really good, that maybe t of x is simply cosine of x in disguise. And indeed, because this is a particularly nice example, it really will be cosine x. This is another way to write cosine x. You can even think of it as it's an alternate way to even define cosine of x. That's kind of weird. We've defined cosine x in terms of circles and angles and triangles and things like that. But you can actually use this as a definition of cosine. But let's back up for a second. One of the cool properties of cosine is that it has some nice derivatives. And I want to show you, if we make one more assumption, it's another bold assumption. Suppose we assume that we can differentiate t of x, what's called term by term, just as if it were term by term, as if it were a polynomial. So it's true that the derivative of a finite sum of functions is the sum of the derivatives, but it's not obvious that the derivative of an infinite sum will be the sum of those functions. But let's assume that we can do that. Then let's see what happens. T prime of x, the 1 goes away, and something nice happens here. The 2 cancels the 2 and the 2 times 1 here, and we just get minus x over 1, which is just minus x. Let's just write that as minus x. Okay. Then something nice, the similar thing that's nice that happens here, we've got 4x cubed, but that 4 cancels the 4 and 4 times 3 times 2 times 1, and that just creates a 3 factorial. Minus, and then again, 6 goes to 5, and the 6 cancels, and you get a 5 factorial. And that pattern is going to continue. Right here, instead of this guy, we're going to get 2n minus 1. A 2n will come out, but that just demotes a 2n factorial to a 2n minus 1 factorial. And then here's the part where we're being bold. We hope that the pattern continues and that the derivative of an infinite sum, we hope, would be the infinite sum of the derivatives of the individual terms. Well, you should think about it for a second. What should that be? If 2 of x really is cosine x, what have we just written down the power series for? But I want to keep going. Suppose we don't even know that there's this other function that's a pair to cosine x. Let's take another derivative. You get minus 1. And then you get 3x squared over 3 factorial. Ooh, you get a cancellation. It's a super common thing with factorials to see this kind of cancellation. 5x to the 4th, but then it cancels to this guy. Plus dot 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 plus. And then you get 2n minus 2. And the 2n minus 1 cancels, and that demotes this to a 2n minus 2 factorial plus dot dot dot. Okay, I'm going to put a minus in front of that and just switch all the signs. And we're going to discover something really nice. This should look really, really familiar. The first 3 terms should look exceedingly familiar. Gosh, we've done this a lot. Okay, and then that just changes the sign, so I'm just going to change that to change the sign. This should look exactly like this, except wait a minute, this term, sort of the general term has changed, but all that's happened is I just switched to talking about the n minus first term instead of the nth term. This is exactly the same pattern, just one term previously. This is exactly minus, oops, I should have an equals here. This is exactly minus t of x. Hey, that's interesting. Even if we had never heard of cosine before, as long as we believe that this infinite sum actually defines a function for all x and that derivatives work term by term, which are 2 big assumptions, we've created a function that satisfies t double prime of x. equals minus t of x. That is something that's true about cosine. And it might be why in a particular problem you care about this function. You might be solving a differential equation that says, I want a function whose second derivative is minus itself. Okay, so this is a good example of how power series can be pretty wonderful. Simply by creating an overgrown polynomial with a certain pattern, we've created something that has some really good calculus properties. So we're going to discover that in this case, at least, all the good things are true. You can differentiate this term by term. It does define a function. It is equal to cosine x. And that's true for a lot of our library functions. However, it won't take us too long to discover that you can write down some nonsensical statements if you're not careful. There are a lot of summations you can write down that really don't make any sense. For example, if I write down 1 plus 2 plus 3 plus 4 plus 5, and you try to make sense of that, that's not going to give you a finite number. And it turns out that exactly this kind of summation is something that we will be tempted to try to assign a finite number to if we're not careful using power series. So we really will have to be careful, and that's why we have to go back and do a lot of grunt work to make everything rigorous.